Yeah, so let me start by thanking the organizers for inviting me to give me the opportunity to join this wonderful conference. So I don't remember what the talk was. Titled. Elliptic units and the elliptic gamma function, or something equivalent. Yeah, so this is really the second part of Pierre's talk. So of course it's joint work with Nicolas and with Pierre. Okay, right. So my goal in this talk is to give, well, sort of a complement to Pierre's talk. So what I want to do is explain exactly how one, starting with a complex cubic field and some additional data, one produces a number that we conjecture to be a unit in an abelian extension. And then I want to state this limit formula that Pierre mentioned briefly at the end. So let me start by, in particular, I'm going to spend some time talking about these properties of the elliptic gamma function that Pierre introduced. And so for that, I want to start with imaginary quadratic case, like other speakers of this conference, because I want to emphasize the analogy between our conjecture and what one does for explicit class field theory for imaginary quadratic fields. The analogy is very strong. So, okay, so the key player in the explicit class field theory for imaginary quadratic fields is the theta function, which already was introduced in Pierre's talk, which is a function of two parameters. So here, z is in C, and tau is in the upper half plane H. And so it's given by this infinite product. So it looks like this. So there are these two variables, q tau and qz. Q tau is e to the 2 pi I tau. And qz is e to the 2 pi I z. And so you see this is an infinite product, but we're taking tau in the upper half plane, which means that each factor tends to zero quite fast as n increases. So this is absolutely convergent for all these values. And so in particular, it's holomorphic, and it has simple zeros exactly at when z lies in L. And it also has these transformation properties that Pierre was talking about. So when we add 1 to z, well, z only appears as qz here. So of course, that stays invariant. Now, and when you add tau to z,
it's a less scratchy piece of chalk.
sure.
So
You are.
I'm going to have to leave.
Should be better.
Okay. Oh, yes, very nice. Okay. Let's see.
Great.
Yeah, much nicer. Thank you. Okay, so those are the two properties that already showed up in Pierre's talk. And so now the connection to explicit class field theory is that if one chooses tau to be a CM point, and one chooses an auxiliary ideal, A of its ring of integers, then one can do the following thing. First, let's consider the lattice z tau plus z defined by tau. And because I'm assuming that tau is a CM point, I can look at the quotient of C by L, which is an elliptic curve that I would call E. So the endomorphisms are now ring of integers. Okay. Wait.
Assumption on tau.
Yeah. When I say CM point, I mean this.
Okay, so it's not just some order, it's all.
Yeah, no, let's take the full ring of integers. Yeah, so here K is imaginary quadratic. And so now one considers the following function, which is not which is now a function only of z because I have fixed my tau, and which consists of this quotient, say L, 12 times the norm of A. And here z of A inverse L. So I'm taking a quotient of two theta functions, but they are theta functions for different lattices. I have a lattice L that I fixed, and I then have a bigger lattice, which I obtain by multiplying L by A inverse, because L is an OK module. And so, and then I raise them to these different powers. And so it's very easy to check using these properties here that this function now has the advantage over the original theta 0, that this is doubly periodic. And so it defines a meromorphic function on this elliptic curve E. And in fact, then what I can do is the following. Let's take another ideal F. Co-prime with A. And now let's take a point, P, that is in the F torsion, except for 0. And so, well, the divisor of this function is very easy to describe. It's supporting on the A torsion. And so I can evaluate this function theta A at P, and I will obtain a non-zero complex number. And that non-zero complex number turns out to be in the Ray-class field of conductor F. In fact, it's an F unit. So this is the Ray-class field. Okay, so this is a classical fact, part of the theory of complex multiplication. It's also true that one has control over the Galois action on these units.
Furthermore, congruent to 1 mod A or something.
Oh,
Which of the primes of A? Yeah, it's okay.
Yeah, yeah, I don't know. Maybe, yeah. I'm not sure. And a relation with the L value. Okay, so this is basically the classical theory. And so I want to point out a little bit how to think of this theta function geometrically, which goes as follows. One takes this group I will call gamma 2, which is just a group SL2Z semi-direct product with Z2. And now I can do the following. So I want to think of functions depending on two variables, Z and tau. Tau is a variable in the upper half plane. And on the upper half plane, I have a certain line bundle called the Hodge bundle. And so I will denote by X2 the complex manifold given by the total space of this Hodge bundle. So this is now a two-dimensional complex manifold. And so here I parameterize somehow. Z is the fiber variable and tau is the base variable. And so gamma 2 acts on this. So SL2Z acts on H, but I also have this copy of Z2 acting on the fibers of L additively. And so this semi-direct product acts on this total space. And if I take gamma in gamma 2, then I can look at what happens when I evaluate theta 0 at Z and tau translated by gamma. And what happens is I get a formula like this. So I obtain again theta 0, but multiplied by this, by a factor like this. And this thing here is a polynomial in tau with coefficients in Z. E pi I times a polynomial. So in fact, another way to rephrase this is that theta 0 is a section of a line bundle on X. And what is this line bundle? Well, sorry. What is this line bundle? Well, I have this map sending an element of gamma 2 to this quantity here. So this thing happens to be a cohomology class of degree 1 for the group gamma 2, valued in the group of multiplicative group of holomorphic functions on X2. So this is a group that classifies line bundles on this quotient. That's yeah. And so this condition here says that we're writing this cocycle as a co-boundary. And so this, by definition, this is a section of this line. Okay, so that's my review of how the theory goes for imaginary quadratic fields. So now I'm
Probably move it. I think they may have fixed the boards by now.
Well, I was just told that is that okay? If I was thinking of sticking to this board so everyone can see, but
We'll do that now.
I think Grant told me that I was
Right now?
right before my talk. Is that okay? Oh, okay, okay. Okay, so now I want to talk about complex cubic cubic fields. Okay, so let me review some of what Pia said. So now I'm going to look at a certain function of 3 variables. Z will still be a complex number, and tau and sigma will be in the upper half. And so this function is this elliptic function. Yeah, talked about. And it looks like this. Function of these 3 variables given by this infinite product. So J and K are integers that vary independently from 0 to infinity. And then I take this product here. Tau, J, let me get this. This one. With sigma, K plus 1. Use Z. Index. Okay, so it looks like this. And then basically for the same reasons as convergence for the previous infinite product, this converges absolutely for these values. And so I think Jean was asking about what happens when tau and sigma are allowed to belong to the lower half plane. And the answer is you can extend it by a formula that basically says that if you replace tau by minus tau, you get 1 over gamma. So still an infinite product, and there is a shift in the variables there. So it's really just for convenience that one is choosing this domain. Okay, so right. So the first thing I want to talk about is how this elliptic gamma function is an analog of this theta function here. And so I want to describe a setup which is not due to us, understanding it in some sort of geometric way. So, but before that, let me talk about this automorphy under this group that I will call gamma 3, which is the group SL3Z semi-direct product with Z cubed. And so this is really due to Felder and Barchenko. In a paper in 2000. Okay, so for that, to describe the automorphic properties, I have to introduce a slightly more general version of this elliptic gamma function, and then we'll see later in the talk why. And so let me talk about that. So in fact, I think it's less confusing to think not of Z cubed, but of a rank 3 lattice. So L is really Z cubed here. We're also going to fix an orientation, by which I mean, so from the top exterior power of L, one chooses a generator. We note the orientation by det. Okay, so it's just one of the generators of this top exterior power. Okay, so construction goes like this. So let us fix two linear functionals on L, A and B, which I will take to be linearly independent. Okay, then one gets the following very simple geometric picture. So I'm going to draw L tensor with R, which is just R3. And inside this L tensor with R, I have two hyperplanes.
So when you say it's a lattice, is it sitting inside some ambient space, or it's
No.
just some?
It's just
some
yeah, it's just
isomorphic to
free abelian group of rank 3.
Yeah, okay.
Yeah, because okay, later our lattice will be a fractional ideal in the complex cubic field, and it doesn't have to be embedded. Right. So I get the following. I get two. If I choose two linearly independent functionals A and B, then I get two planes in this three-dimensional space, which are the kernel of B and the kernel of A. I also get a line where these two planes intersect. And inside that line, I get a particular vector gamma. And so what is that vector gamma? So gamma is in the lattice, and it's primitive. But I still have to choose one of the two generators. And so I can choose one by using the orientation. So I can look at this. This is a linear functional on this space, hom LZ. And so I want that functional to be a positive. In any case, given the orientation on L, I can choose a direction on this line. And I also get 4 regions, which are the complement. If you remove these two planes, the resulting space has 4 connected components, or the 4 quadrants, let's say. And so I will call them something like this. This is what I will call C plus minus, something like this, C minus plus, which are essentially the ones that appeared in Pierre's talk. So here, C plus minus consists of elements in your lattice that lie on certain, so you specify if the values of A and B, well, the value of A should be positive, the value of B should be non-negative. Sorry, non-positive. Similarly for this. Okay, so all that is elementary. This all comes just from choosing two linearly independent functionals, A and B. And so now I'm going to define a function. And for that function, that function depends on 2 more parameters. One is a vector in the complexification of L, and the other is a complex valued functional on L. So given all this, I'm going to define this function called gamma AB. H sigma in the lattice L. And so what is it? It's again an infinite product. And so I look at, so I forgot to say that these two C plus minus and C minus plus, they are sort of these two regions that I tried to explain here. But notice also that these regions both contain this line generated by this vector gamma. And so I'm going to write down an expression that makes sense for any lambda in here, but it's invariant under Z gamma. And so I can think that I'm indexing given by this expression here into the sign, right? And it's 2 pi I sigma of gamma. And now I quotient by the lambdas in the minus plus. Okay. So that's it. Basically, I'm looking at the product over elements of the lattice, but modulo Z gamma, so it's really a rank 2 lattice that I'm looking at. And I have some inequality conditions given by A and B applied to lambda should have the right size. And right, so now this converges for, to make sense of this, so I have to, these factors depend on choosing a linear functional valued in the complex numbers that I apply to an expression lying in the lattice. And so, right. So this converges when sigma belongs to a certain intersection of opens, UA and UB inside. Okay, so basically this condition that sigma should belong to UA and UB inside here is the condition becomes the condition that tau and sigma should lie in the upper half plane. So, okay, I didn't specify that. If you choose A and B to be the standard basis vectors on Z cubed, then this expression here recovers exactly this doubly infinite product. Okay, it's really so it's basically, you can think of this as this infinite product, but where instead of specifying that you want exactly, this quadrant, the first quadrant, you give yourself a little bit more freedom to where you put these planes. Okay, and so we need some condition to ensure that it converges corresponding to this, and that's this condition that sigma should belong.
You didn't write down the definition of UA.
I didn't write it, but it's what you think it is. I mean, this thing should have positive imaginary part, so that this tends to 0 and then converges. It's nothing more than that.
We should think of this lambda really as range over rank 2 lattice, right? Because you're modding out by gamma.
Well, you could, but then you will lose the SL3 equivariance properties.
Yeah, okay. But I mean, when you actually, like, if you were to compute this product, it's.
Of course, yeah. If you compute the product, you compute it using the. So another thing I didn't say is that this thing can always be written as a finite product of the gamma functions I had at the beginning, of the elliptic gamma functions I had at the beginning. And so, yeah, you're right. You should think of it as a rank 2 product, but it's important to keep the rank 3 lattice in mind. So, right. Okay. Okay, so now that I have defined this thing, I can tell you in a much nicer way what are these automorphic properties that this product has. And the main one looks like this. Now, suppose that you take 3 functionals on L. Then you can consider gamma AB times gamma BC times gamma CA. And it turns out that this is BC. Maybe I should put a page, sorry.
But did you tell us what P was?
No, I didn't tell you what it is, but it's called P because it is an explicit polynomial in H with coefficients in, let's say, Q, A, B, C. I mean,
Does that mean?
okay, I mean, yeah, it's a polynomial in H given by an explicit formula. Okay, depending, and the coefficients depend on A, B, and C. Okay, it's also a cubic. It's a cubic polynomial. Okay.
It must be rational. It wants to be rational.
Yeah, that's right. So yeah, it's a bit like, well, I didn't write for the theta function. It's also the same thing. I mean, yeah, in some sense, the coefficients depend rationally on A, B, C. Okay. Right. Okay, so now I can, so maybe that was the first thing. The second thing that's important is that if I choose G in this I choose G in this group gamma 3, then I can, then this thing is equivariant. So this was also mentioned briefly by Pierre in his slides. G sigma L. This is the same as, so I can act on these functionals A and B, and also there is natural actions on sigma and H. If I act on all of them, then it stays invariant. Okay. So those are the two main properties. Okay, and so now I can talk a little bit about this geometric interpretation of this. And this is, like I said, it's not due to us, it's due to Felder and requests C and Zhu. And goes like this. So one has this space CP2 minus RP2, which is somehow a higher dimensional analog of the upper half plane. And on this one has some action of SL3. Just because CP2 is the space of lines in some three-dimensional vector space, and so SL3 acts linearly. And on this space, I have a natural bundle. Which bundle? Where I can let this group gamma 3 act.
You probably said this. So what is the action of gamma 3 on L? Because it has the Z3 in it, right?
Yeah, so the Z3 acts by translation by these periods 1, tau, and sigma. Okay, so maybe it will clarify things if I explain that the tau and sigma in Pierre's talk are the projective coordinates for some point in this CP2 minus RP2.
Okay.
And so when you have an element, so SL3 acts on this sort of projectively, but there is also a coordinate in this line where you can add. So basically a point on this line corresponds to a linear functional on your lattice. And so you get 3 periods where you're applying and you're translating.
So upstairs there, you fixed a basis for L, like when you have GA, GB in the upstairs, like above where you wrote geometric interpretation.
Yeah, so already, so yeah.
Above.
Yeah, here.
Yes, like right below that.
Here.
There you go,
Oh,
yeah.
that's right. Yeah, sorry.
So there.
Yeah, it's
you
true.
You fix some basis of L in order to, I mean, or is the action is not.
Yeah, of course. Yeah, if I want to, yeah, okay, I'm being a little bit slow. Yeah, so here I'm assuming that I have already fixed a basis of L, so that I can really talk about SL3Z acting on it. That's true. Yeah. I mean, I could write, okay, this identity, this thing that I wrote makes sense. For example, if you wrote
Yes.
G is in there, that's fine. And this is SL3Z.
Yeah, but then you have this Z3.
But you also have this
that's
Z3, which I'm not emphasizing here, but I'm.
Oh, wait, but is that because you wrote gamma 3 before? So.
Oh, sorry. Yes, yeah, of course, yeah, sorry, yeah, which will act. So, I mean, it will all the gamma 3 part will only act on this. Am I correct? Yeah, it will only act on this H part.
Okay, but you can't have it act on the, because you can just have a translation by the lattice also. Like
Sure,
you're
that's
choosing a basis.
H is an element of the lattice. H is an element in L tensor C. And so I can add an element of the lattice and obtain another one.
Okay.
That's all. Yeah, so yeah, sorry, yeah, you're right. I did write gamma 3. But yeah, but I think it's correct. Okay, so this is the Fox bundle. And so now what happens is that I'm going to let X3 be the total space of L. And so an element in here, an element in here is parameterized by some coordinate that I will call Z and some linear functional sigma corresponding to the point on the on CP2 minus RP2. So this is in C, and this is in HOM LC. Okay, and right. And so I can write X3 as a union of opens. So these opens are indexed by the linear functionals on the lattice. Yeah, so for each linear functional on the lattice, I get this plane that I was talking about first, and then you can look at the linear functionals for which the imaginary part is positive. So this gives you a covering of X3, which is also an equivariant covering. So if I act here, it's like acting like that. And so this is an equivariant covering. Equivariant covering. Okay. Okay, so I have these opens covering X3, and I also have these functions that I talked about before, e to the pi I EABC. And so before I said to define these functions, I have to be in the intersection of UA and UB. And so for this to make sense, I have to be here in the intersection of all these three. So that's a holomorphic function here. And so this identity plus the equivariance means that, in fact, one can think of this as defining a class that I will call E pi IP in H2 of this quotient here. Okay, so what do I mean by this?
You mean that your gamma defines the class and the sheaf is
No,
depending on E.
E to the pi IP defines a class. So for every triple of opens,
Okay.
I get a holomorphic function. Okay. And so what you're thinking of is H1 of O star is given by a collection of transition functions where given 2 opens, you have a holomorphic function. But now here I have 3 opens. And so it doesn't define a class in H1, it defines a class in H2 in some Čech complex. So you write down the Čech complex for this covering of X3. And when you look at the H2 thing, what you need is for any given collection of 3 complexes, you need a holomorphic function. And they need to satisfy a co-cycle relation, which these guys satisfy.
See. Okay.
So this is a class in H2 of this. But you're asking about H1, and so this is a similar story to what I just explained about the theta function. There is a line bundle, and then theta is the section. And so here there is this thing is
Gamma should give you
a gerb, exactly. And gamma gives me a section.
Yes. Yeah. So
Which is an H1.
Yeah. That's what I was expecting it is.
Okay, so
What was the gerb? This is that?
yeah,
The gerb over what?
right. Okay, so right, so yeah, thank you. So this is a quotient that's very bad. And so what when I write this is not, I'm not going into the details of what I mean by this, but the idea is that you can you have this group gamma 3 acting on X3. The quotient, the naive quotient is very bad to think about. But what you can do is think of the equivariant. Once you have an equivariant covering, you can build a double complex formed by cochains of this group gamma 3 valued in the Čech complex of this thing. And then the total cohomology of that is a little bit like, you can think of it as the correct cohomology to think of for this quotient with values in this sheet. Okay, so what I'm saying is that maybe.
So is there some property that this function satisfies that makes it give rise to a
Well,
cycle? Like
yeah, so if you choose or functionals, then there is some relation.
Yes,
But
that's
but
what
there is also an equivariance relation if you apply G to A, B, and C. And so I'm packaging all these relations into a statement to say
okay.
that this is a class in H2. And you should understand this as saying both something about how these functions behave on these opens, but also about how gamma acts on them. Okay, so I mean, yeah, let me not
There's
go.
something you have to prove to make that.
Yeah, exactly. Yeah, there is enough structure to make this statement true with the appropriate definition.
Yeah.
The same as just the equivariant cohomology of
Yeah.
the sheet.
Yeah, it's
Exactly.
yeah, it's the equivariant cohomology, but I mean the equivariant Čech cohomology with respect to the complex I'm taking here.
Yeah.
But this is a good covering. So okay, so that's what that class is, and so now gamma AB is so similarly to what was discussed in other lecture. Gamma AB is now a meromorphic function on the intersection of these two things. And so this defines a class in H1 of this thing, gamma 3, mod X3, in M star, mod O star. So why in M star mod O star? Because if you take this relation and you pretend that you kill the O star thing, then you get a cocycle relation for this thing. Okay, so this defines a class here that I will call gamma that maps to this class E pi IP under the connecting homomorphism from this to that. Okay, so that's in that sense, it's analogous to the theta function. Okay, so now I can tell you, so I will come back to this picture when I explain how it helps us think of the elliptic gamma function as related to Eisenstein series. But before that, let me go back to the complex cubic fields. Okay, so I'm going to take K, will be a complex cubic field. So now I'm back to the setting in Piax-Stock. So K has a real embedding, sigma R, and two complex embeddings that I denote by sigma C and sigma C bar. Okay, so I fix one of them and I call that one sigma C. And so now I need some additional data consisting of ideals A, B, and F. And so it should be, okay. It should be co-prime, and there are some additional conditions on the auxiliary ideal A that may don't matter exactly what they are. A should be co-prime to both 6 and the norm of F. And it should be of prime norm. But in any case, some very mild conditions on these ideals. And so I'm going to be interested in KF, which is the narrow Ray class field. Okay, I'll come back to that. Right. And so I'm going to assume that KF is totally complex. And the reason is that, well, we can define our numbers even when it's not, but then it turns out that it's just equal to 1. And it has to do also with wanting to be in the rank 1 case of the star conjecture. So those are data. Right, okay, so now I'm going to tell you how to use the elliptic gamma function together with this data to define a number in this generality. So, okay, so first we need a rank 3 lattice, which is just going to be F inverse, fractional ideal. This is of rank 3, and this lattice has an action of a group that I will call OF star, which is just, so the group of units of K, because K is complex cubic, is of rank 1. And so I'm going to look at the units that are congruent to 1 mod F. And so this is now generated by a unit that I call epsilon. So here I'm going to take the unit whose the generator epsilon is the one whose real under the real embedding lies between 0 and 1. And so we need to, okay, we want to evaluate these elliptic gamma functions. And so we had to choose some element in the complexification on the lattice, some functional. So I need to make some choices. So first of all, I will take H in L, also Q, plus some congruence conditions that I don't want to go into, but that can always, there are always H's. So satisfying some congruence conditions with respect to these ideals, A, B, and M. So this is the analog of the choosing a torsion point in the elliptic curve that we, in the imaginary quadratic field case. And right. And so once I do this, there is a little lemma that, remember, I introduced these elliptic gamma functions that depending on choosing two linear functionals A and B. So I have to choose these A and B somehow. And I'm going to choose them so that H points, so maybe it's easier to draw the diagram. So again, I have, so this is the kernel of A. And I'm going to choose my B to be epsilon times A, where epsilon is the unit. And first of all, I want to choose A such that the intersection of these two planes is a line containing H. And it turns out that there is basically a unique way to find such an A. There exists a unique A in here, such that, so A of H and epsilon A of H are 0. And well, there is a, that would determine A up to sign, but in fact, the sign can also be determined by saying that yeah, so I have fixed an embedding of K into C, and so that embedding gives me a functional that I can restrict to the kernel of A, gives me a map from the kernel of A to C. And I want this to respect orientations. So I should have said that because I have fixed an, so I'm going to fix this complex embedding. And so this lattice of rank 3 is naturally oriented because I have this embedding. Okay, so yeah, my lattice's fractional ideal is naturally oriented. And now I can tell you what number is that we are interested in. It's this number. So it's quotient. H and sigma C and FP inverse. There is normal thing. And here I divide by it. So that's the That's our number. Maybe I should call this just to make it clear on the dependence. So this is a number that one obtains once one chooses these three ideals and this choice of torsion point H. It's a quotient of two elliptic gamma functions of the type I discussed before. My A and B's are always related by an action of this fundamental unit epsilon. And well, remember these gamma functions depend on choosing a point in the complexification of the lattice, which I just mentioned. And also one needs a linear functional on the lattice, complex value linear functional, but we already have one. It's just given by our complex embedding. Sigma C. Okay, and so the important thing is that these are convergent infinite products, and H is chosen to guarantee that we are away from the zeros and poles of these infinite products. So this is always a well-defined non-zero complex number.
So can you think about this as the cap product between your cohomology class and the fundamental class associated to the unit?
That's a good question. Yeah, so there is an issue here with evaluate. So here I said this defines a class in here,
Yes.
right? But to obtain a number, you would actually, if you want this to work, you would have to somehow leave this to just M star so that you can actually obtain a number and not a number up to. So I hesitate to phrase it in terms of this exact in this cap product way because yeah.
Maybe you can do, okay, we'll talk about it.
Yeah. I mean, okay, it's true that one is evaluating some co-cycle and then one gets some meromorphic function in some space and then one evaluates that function somewhere. That this is true. And one evaluates that function at a point which is fixed by the matrix, which is given by the input. So in that sense, yes, but yeah. Okay, so do I have about 15 minutes left? Sorry, no. Yeah, no.
That's fine. I don't remember exactly.
Okay. Okay. Okay, so I guess I'll say 15 minutes. Okay. Right. Okay, so now I can state the conjecture. Okay, the conjecture with Nicolas and Pierre. So I'm going to fix a complex embedding of the ray class field that extends my fixed complex embedding of K. And then the conjecture says the following. First of all, this number so I mentioned that I had to choose some vector H, and all I was imposing was some congruence conditions on for H relating to A, B, and F. In fact, and this is basically a numerical conjecture. This is this number is independent of H. It's independent of H, and it's also a unit in KF. So these are the units that Pierre was presenting in his talk. Okay, so that's the first thing. The second thing is you can ask, what about the valuations of that unit with respect to other Archimedean places? So if you look at that at this unit in AF, well, this this tells you what it is for this embedding. It's given by this formula, by this infinite product. If you embed it by an embedding of KF into C that extends the real embedding, then the conjecture is that you obtain a number of absolute value 1. And finally,
Then can F be the trivial ideal?
no, because I said F is totally complex. KF is totally complex.
Two would not be.
Yeah. No.
K of F can be totally complex if F is the trivial
No,
ideal.
but it could be you could get the Hilbert class field of it.
Yeah.
narrow Hilbert class field.
Could be.
No, but it's a cubic field, no? I mean, you have minus. What am I saying?
I'm asking this because 2 would not hold true for the Stark unit if F is trivial.
Well, I certainly don't want F to be
Okay.
trivial.
Let's stay away from that then.
Okay, maybe I'm. Okay, we can discuss it later. I'm getting. But certainly, yeah, we are not allowing F to be trivial, and maybe it was not enough what I said before about what I'm imposing on KF. Yeah, and okay, so that's 2, and then part 3 is a Galois reciprocity law. That we choose an ideal coprime. Let's see. Then you have the Artin symbol, and you can apply it to this unit. And the answer should be this unit where you multiply B by C.
So does condition 3 imply condition 2?
I
you know how to
don't
prove
think so
that?
because there are many embeddings. No, I don't see how. This is about places.
Yeah, I'm saying what you want to do is you want to take a C that represents complex conjugation in the place above the real place and show that. Okay, we can talk about it later.
Oh yeah, I see what you're saying. Yeah, maybe.
Probably, I'm guessing 3 implies 2. But we can
Yeah,
talk about it
maybe.
later.
Okay, yeah, that's great. Yeah. Okay. Okay, and then of course, this looks very familiar from the Stark unit. So of course, as a corollary of the conjecture, if you compare these statements with Stark's conjectures, what you get is that what we are getting really is a formula for the Stark unit in the, in the field of conductor F, Galois twisted by this element of the.
That's just the Stark unit with that A being your set T.
Exactly.
Yeah, yeah.
Exactly. Yeah. So I said A had to satisfy some conditions which guarantee that. Okay, so that's So
Please follow from 1, 2, 3. Where do the all functions come?
so this is a unit in this field. You are it doesn't follow. Okay, yeah, thank
We
you.
haven't done.
It will follow from the theorem about the state, which gives you the valuation above the complex places above the. Yeah. So I didn't say what is the valuation above complex places above sigma C because that's a theorem. So I'll say that's a theorem. Yeah. Garage of next theorem. Okay.
We're predicting the signs at W above the real place.
They are not just signs. They are really. It's totally complex. So it's just a number on the unit circle. Oh, no, but it's a great question. We don't know how to. We don't have formulas or like an analogous formula that tells you what does this number look like under one of these other embeddings. Okay, so right, so finally I can state this limit formula. Right, so yeah, so the conjecture specifies what the valuation is of this number that allegedly lies in KF for every place except for the ones above sigma C. And so for the ones above sigma C, we have a theorem which says the following. Let me introduce these partial zeta functions. So if I have 2 ideals F and B relatively prime, I can consider the partial zeta function given by this expression. So I sum over ideals whose class in the narrow Lie class group of conductor F is a fixed class. And I also introduces a sort of smoothed version of these theta functions that already appeared in Summit's talk, which is given by this linear combination. So when an auxiliary ideal A, one considers this.
You made 1 minus S or something. That S equals 0 doesn't.
That's
make
equals 0.
sense.
Yeah.
Okay.
Is this worse than? putting one minus
Yeah,
S here?
yes.
Okay.
Yes.
Okay.
If you want to consider any other values.
Okay, so I can correct myself real time and consider this because we're going to take S equals 0 anyway. Okay, and so the important thing is that this vanishes at S equals 0. And so now we are not in the case of that in Summit's talk. We're in this rank 1 case. And so the theorem is that the derivative of x at 0 is the logarithm of this number. So that's the formula. It's really analogous to the Kronecker limit formula, except for complex cubic fields. And so, yeah, so I mentioned before that part of the conjecture is that this number does not depend on h. So yeah, this proves that the modulus of this number does not depend on h, but we don't know how to upgrade that to actually. And yeah, so I do have about 5 minutes left, I think. I'm not entirely, okay, I mean, yeah. Okay, so maybe I'll explain a little bit what's the idea of the proof, which is where this geometric interpretation plays a role. Because, so the idea is the following. So I talked about this symbol here, which is a quotient of some complex manifold by a bad action of this group. So I only wrote it down inside some cohomology group, and so one could really define that cohomology group using some equivariant Čech cohomology, something like that. But one really has the feeling that one should consider some interesting objects over this space. And so there is a standard thing. If you have a nice space and a group action, and the group action is bad, then you take the homotopy quotient, not the naive quotient. And so the homotopy quotient means that you first multiply the space x3 by some nice space, and then you take the quotient. So what is this nice space? So S3 is just contractible space where gamma 3 acts freely. It's basically the symmetric space for SF3R. So once one wants to somehow now look at objects over this quotient, and so this is a little bit closer to the world of automorphic forms, except one has this additional variable x3 given by this CP2 minus RP2. And so
Did the Z3 part act on S3?
yeah, thank you. Sorry, gamma 3 was a semi-direct product, so I have to take that. Thank you. Yeah, I keep thinking only on the SF3 variable, but you're absolutely right. Okay, so the idea, very briefly, is the following. We want to prove this identity. And so what we're going to do is compute 2 periods of a certain Eisenstein series living on this state. So the proof goes like this. Okay, so one introduces a differential one form that one then integrates onto different chains living in this space. So basically, one looks for some form that I will call Eisenstein, which is a one form living on this quotient. And one would like this one form to one would like it to be like a regulator for this class gamma. So the integral on some chains should be related to log of gamma. So it has like a, and so it turns out that if one works just with S3 mod gamma 3, which is the usual setup of locally symmetric spaces for SL3, there are natural two forms, and these underlie things like the Klingon-Ziegel theorem, and there are natural closed differential forms of degree 2. But that's not enough, because here we're in the complex cubic case, the chains are naturally one chains. And so one needs to somehow, by adding this variable, one can sort of make the form degree of this degrees. And that's basically the idea. And so maybe I'll just say that maybe I'll just say this. So one defines this Eisenstein series. And so the fact that, so it's not difficult to attach to a unit to attach a closed geodesic in this space. That's basically the unit corresponds to a 3x3 matrix with determinant 1, and then that naturally defines a closed geodesic here. And so finding a one form whose integral over epsilon gives this is not difficult. It's a well-known thing that toric integrals of Eisenstein series give L values. That's basically it. What's interesting is that, so maybe I won't go into more detail, but I'll just say that this uses, one can basically deform the integration of using the geometry of the symmetric space S3 to argue that that integral is the same as some other integral over some something which looks like a generalized modular symbol. And somehow what happens is that once one has moved to this other chain, it came to us a bit as a surprise, but basically here is one integrating some sum over rank 3 lattice, but there is a lot of cancellation, and one ends up having a sum over cones, which is sort of what this looks like. Okay, but maybe I think I should stop. So thank you.